Hi, I want to talk about how we can arrive at a situation of finding discrete energy levels in quantized systems by going back to the problem of having a standing wave on a string fixed at two ends and applying the resonant modes that we see to a particle analog, some sort of particle of energy. So if we have a standing wave on a string, we ended up getting resonant wavelengths. And those resonant wavelengths had to be equal to 2 times the length of a string divided by an integer, where n could be 1, 2, 3, 17, whatever. Well, by de Broglie's equation, the wavelength has an associated momentum. The wavelength is equal to Planck's constant divided by the particle momentum that we would have. So our particle momentum would be Planck's constant divided by the length of the wave. And the momentum of an equivalent particle is related to the kinetic energy of that particle if it's massive. For a massive particle, the momentum squared divided by 2 times the mass is our kinetic energy. And since P equals mv, substituting mv squared in for P, or m squared v squared, gives us 1/2 mv squared, the normal way we see of writing the kinetic energy. Well, we have no potential energy associated with this sort of wave. So our kinetic energy is just our total energy. So our momentum would be equal to h, our Planck constant, divided by the length of the wave that we're dealing with. And that momentum is going to be the square root of 2 times the mass associated with our particle times the energy of our particle. So if I plug in my discrete wavelengths that I had 2 times the length over n, then I get n times h over 2 times the length is the square root of 2me, or 2 times the mass of our particle times the energy would be n squared Planck's constant squared divided by 4 times the length of that wave system squared, or the discrete energy levels available to that quantized system. A quantized system is just a system where there are discrete energy levels n. In this case, I would have energy levels equal to n squared times Planck's constant squared divided by 8 times the mass of a particle that we're dealing with. And in quantum mechanics, we're really always dealing with electrons and the length of a region in which that electron is behaving like a wave squared. We'll talk about a more proper way of determining these energy levels for electrons trapped in a small region a little bit later. Thanks for watching.